Okay, we're back. And where we left off on the first video was the accuracy and precision. We were looking at page 20, and we were looking at how the accuracy and the precision of the person on the far right that shot those arrows, how they're all grouped very tightly, making them precise, and they're all on target, hitting the bullseye in the center. That's where we want to be when we make our measurements. But again, you can be accurate and not precise. You can be precise and not accurate, or you can be both accurate and precise. Precision is dependent on the instrument you're using, and accuracy is dependent on the person that's making the measurement. Okay, so that's the difference between accuracy and precision. Now, something that's totally new to you that we will review on Friday for sure, because it is new, is significant figures. The first part is real easy. Actually, significant figures is not that hard, but it's a little confusing in the beginning. What is significant figures? We use this in chemistry. We use it. You can use it in a lot of sciences, physics, and stuff. Chemistry is where it's used the most. And the reason what significant figures are is about showing the person that's looking at the problem, indicating to them the level of precision that you used in making your measurements. Okay, so the precision of an instrument determines the number of significant figures we are going to report when we make a measurement. We have to memorize the following rules. You have to memorize these. Number one, a digit within a number is considered to be significant. A digit within a number is considered to be significant if it is a non-zero, or it is a zero between two other significant figures, or it is a zero at the end of the number and to the right of the decimal point. Again, these are the rules. If it's a non-zero, it's a significant figure. If it is a number between two significant figures, it makes that number significant. It's in between the two significant figures. And if it is a zero at the very end and to the right of the decimal, that is a significant figure. So let's look at example 1.5 to see if we can determine what's significant and what's not. If you look at page 21 on your book, you'll see, count the significant figures in the following numbers. So the first one is 3.234. Okay? It has four significant figures. Why? Because all of them are non-zeros. And remember, rule number one says if it's a non-zero, it's a significant figure. So number A is 3.234. All four of them are non-zeros, therefore four significant figures. Let's look at B, 6.016. What is significant? Well, 6 is. The 0 is as well because it is in between the 6 and the 1. And both of those are significant. That makes the 0 significant. The 1 is significant and the 6 is significant. So there, the answer is 4. All four of them are significant. Let's look at the C, 105.340. 1 is significant. The next 0 is significant because it sits between a 1 and a 5, and both of those are significant, so 0 is significant. 3 is significant because it's a non-zero. 4 is significant because it's a non-zero. And the last 0 is significant because it is the last number, and it's to the right of the decimal. And that was rule number 3. It says if a 0 is at the end of the number and it's to the right of the decimal point, it's significant. So in this answer, the number of significant figures there is 6. What about D? We have 0.00450010. How many significant figures are there? The first 0 is not significant. The second 0 is not significant. The third 0 is not significant. The 4 is. The 5 is. The next 0 is because it sits between the 5 and then to the 1 further to the right. It's in between. Then the next 0 again, that one is significant too because it sits between the 5 and the 1. And then the last 0 is because it's to the far right, it's the end of the number, and it's also to the right of the decimal. So here the answer is going to be 1, 2, 3, 4, 5, 6. So D is 6. 6 significant figures. Again, if it's a non-zero, it is automatically significant. If it's a 0 between two significant figures, it's significant. If it's a 0 at the end of the problem number and it's to the right of the decimal, it's significant. So look at all four of those again. Apply the rules, and you should be able to determine how many significant figures are in each one. Okay? If you, for grins, we can look at the on your own 1.12 at the bottom of the page 21. Let's look at C. 1.00450. How many significant figures are there? 1, 2, 3, 4, 5, 6. The answer is 6. Why? Because the 1 is significant. The 0 is in between the 1 and the 4. The other 0 is in between the 1 and the 4. That makes them both significant. The 4 is significant. The 5 is significant. And 0 is to the end of the number and to the right of the decimal. Again, apply the three rules to determine what numbers are significant or not. Okay? Now, it gets a little more difficult than that, and we're going to learn that in a second. So give me a minute. Let's move on to scientific notation. Scientific notation is when I have a big number or a really small number with lots of zeros. I want to make it easier to write. I can write it in a way that's called scientific notation, not have to put all these zeros in. So in chemistry, we often report very large or very small numbers because we have such excellent precision in our measurement capabilities. Rather than list all the numbers in one long chain, we can simplify it by using the technique known as scientific notation. So look at example 1.6 in your book. It says convert these numbers into scientific notation. Let's look at E. 0.000875. Instead of writing out those zeros, I could say 8.75 times 10 to the negative 1, 2, 3, 4 to the negative 4. Again, this stuff you should have already known and learned. Okay. What about the C? Let's do C. 234,000. Instead of writing out the three zeros, I could write 2.34 times 10 to the 5th power. Why is it to the 5th and not negative 5? Because I'm not going left. I'm going right when I move my decimal. Okay. Anyhow, this is scientific notation is something you should have already learned in math and be able to apply. Why is it important that we review it and understand it? Because sometimes when we're reporting significant figures, you can't write all those zeros. If I ask for something in significant figures, you have to use scientific notation in order to get the correct significant figures to report. This will come clear in a minute. All right? Let's go to the very last part, actually second to last, using significant figures in mathematical equations. Got to memorize the following rules. So in addition to the significant figure rules, you got to memorize these two rules to apply them in mathematical equations. Rule number 1. When adding and subtracting in a mathematical equation using significant figures, we're going to round the answer so that it has the same precision as the least precise measurement in the equation. Rule number 2. When multiplying and dividing, so we're not adding and subtracting, we're multiplying and dividing with significant figures, we want to round the answer so that it has the same number of significant figures as the measurement with the fewest significant figures. Again, reading that doesn't probably make much sense to you. It's confusing. We can look at example 1.7 to try to understand those rules and apply them. It says a student measures the mass, we're going on page 26, example 1.7. A student measures the mass of a jar that is filled with sand, and it finds it to be 546.2075 kilograms. The jar has a note on it which says, when empty, this jar has a mass of 87.61 kilograms. What is the mass of the sand in that jar? Okay, so if we weren't going to use significant figures, we would simply just take 546.2075 kilograms and subtract the jar mass, which is 87.61 kilograms, and you would get 458.5975 kilograms. And you would be right. Very simple. However, we have to use significant figures. It's a different ballgame because we have to apply those rules. What are we doing here? Are we adding and subtracting, or are we multiplying and dividing? We're adding and subtracting. In this case, we're subtracting. So we're going to apply rule number 1. Remember, rule number 1 says when adding and subtracting with significant figures, we're going to round the answer so that it has the same precision as the least precise measurement in the equation. Out of those two numbers, 546.2075 versus 87.61, which one is the least precise? The least precise one is 87.61 because it only measures it to the 100th place. See that 546.2075? We're out to the 4th decimal place. We're out past beyond 1,000. Much more precise. So when we report our answer using significant figures, we're going to apply rule number 1. We're only going to report it to the 100th decimal point because that's the least precise measurement in the mathematical equation. So take 546.2075, subtract 87.61. If you reported your answer using significant figures as 458.5975, you would be wrong because you didn't report it to the correct number of significant figures. You need to report it as 458.60. Why? Because I rounded it up. 0.5975 is really 0.60, and I only reported to the 100th place because that's the least precise measurement that was in the mathematical equation, to the 100th place. So I only report the answer in the 100th place. Do you see what I'm saying? I used rule number 1 there. Let's go to the second part of the problem. It says a person runs 3.012 miles in 0.430 hours. What is the person's average speed? Well, what's speed? Speed is distance over time. So I got to divide 3.012 by 0.430 hours. That'll give me miles per hour. If I did that, 3.012 divided by 0.430 hours, I would come up with the number 7.004651163 miles per hour. If I wasn't using significant figures, that would be correct. But if I required you to use significant figures, you can't report that number that way because it would be wrong. Why? Because there's too many significant figures. You got to report according to rule number 2. Rule number 2 says when multiplying and dividing, and we're dividing here, with significant figures, we want to round the answer so that it has the same number of significant figures as the measurement with the fewest significant figures. Which measurement has the fewest significant figures? In this case, if you look at each one, the first one, 3.012, has 4 significant figures. The second one, 0.430 hours, has 3 significant figures. How do I know that? Because I applied my rules that I learned a little bit ago. That zero, that first zero, that leading zero, is not significant. It's not a non-zero. It's not to the right of the decimal at the far right. And it's not in between 2 significant figures, so therefore it's not significant. So 0.430, now 4 is, 3 is, and 0 is at the end. The last 0 is, so there's 3. So I want to report my answer to the 1,000th, or the third number. So instead of 7.004651163, it was significant figures, that would be wrong. I need to report it as 7.00. See, I round that. Actually, I didn't round it. I just said use 7.00. Why? Because the 7 is significant. The 0 in between the 7 and the last 0, which is significant because it's to the right of the decimal, it's at the end, that makes that significant. And then, of course, the last 0 is significant. So I have 3 significant figures there, and that jives with the number of significant figures that I used for my measurement for hours, which was 3. So that would be the proper answer, 7. If I reported 7.004651163, I'd be marked wrong. If I reported 7.00, I'd be right, using significant figures. Now, I'm going to require you to do that for the quiz, and I'm going to require you to do that on one problem on your midterm exam. I'm not going to require you to do it on all problems. Some teachers do. And in college, hopefully you'll get a nice teacher, a nice professor if you take chemistry in college that doesn't require it every time. Because there's nothing like working through a problem and doing everything right and at the end report the wrong number with the number of significant figures when everything was done else correctly and you mark it a big X wrong. That's very frustrating. In fact, I wanted to choke my teacher, and I never I never did, but I wanted to choke my teacher plenty of times because he would be marking me wrong. I did everything right except I screwed up on the significant figures. It's very, very frustrating. I'm not going to do that to you. I'm not going to frustrate you and cause you all that pain and suffering. But I am going to make you learn it in case down the road a teacher makes you do it every time. So you're going to do it on the next quiz, and you're going to do it also on the one problem on the midterm exam. And that problem's going to be worth 10 points. It's a whopper. And you're going to have to know how to do it because I want to make sure you know how to do it. But I'm not going to make you do it every problem on the midterm, and then in the final exam, I'm not going to make you do it because I'm not going to frustrate you and beat you up over it because it can be very, very frustrating to get something wrong because of significant figure when you did everything else right. It's very frustrating. Trust me, by the end of the year, you're going to thank me. You're going to thank me for not making you do that. You just don't appreciate yet how nice I'm being to you. But I am going to make you learn it, okay? All right. That is the last... No, there's one more section. And again, I'll review this stuff, this significant figure stuff on Friday because I want to make sure you understand it. The rest of that stuff I probably won't even review because that stuff you learned in 6th, 7th, 8th grade. You should know it by now. Should not have to, I reviewed it, but that's it. We got to move on. What's the last thing in the notes? It's density. Give you a hint. A problem of density is on the quiz and the midterm exam, so I want you to know how to do it. What's density? It's the object's mass divided by its volume. Okay? It's simple as that. You have to know that. You have to memorize that. Density is mass divided by volume. Okay? Oh, another thing, by the way, I'm not going to make you memorize all the formulas that you need for chemistry. I will give them to you. Okay? Except for density. I want you to memorize that one. Density equals mass divided by volume. But all the other formulas down the road that we get, you're not going to have to memorize them. I give them to you because I want you to learn. I want you to be able to apply it. I don't want you to be able to regurgitate some stupid formula that you'll never need again 10 years from now. But the application, the knowledge you get from applying it and understanding how it works, that may be usable down the road for you. Okay, so let's look at the example for density. It's example 1.8. It says in the book, page 30, it says, a gold miner has just found a nugget of pure gold. He measures its dimensions and then calculates its volume to be 0.125 liters. Knowing that the density of gold is 19.3 grams per milliliter, calculate the mass of the miner's nugget. So they give you volume and they give you density, and they want you to calculate mass. So they give you 2 of the 3 parts. How do I do this? Okay, let's see here. Okay, so they gave us, the first thing they gave us was volume, which was 0.125. His nugget had a volume of 0.125 liters. And then he told us the density of gold is 19.3 grams per, is it milliliter? Is that what it is? Yeah, grams per milliliter. Okay? So, he wants to know, the question wants to know, what's the mass of this gold nugget? Okay? So the first thing I got to do is I got to convert this into milliliters. Why? Because this density measurement is in milliliters. And this is in liters. Those are 2 units that don't get together. I mean, you got to compare apples to apples, so you got to convert this. How do I convert this? Well, how many milliliters are in a liter? 1,000. So you set up an equation that says 1 liter is equal to 1,000 milliliters. What happens to my liters? They cancel. What's 0.125 times 1,000? That's 125 milliliters. I didn't have to set the equation up. I could have just moved the decimal 3 places because I know there's 1,000 milliliters in a liter. But I set up the equation and we did it that way. The answer is 125 milliliters. Now I got apples to apples. Remember, density equals mass over volume. I have density and I have volume. I need to solve for mass. What do I got to do to this equation? Well, I got to use algebra to rearrange the equation to solve for the unknown. How do I do that? Well, mass equals d times v, right? I rearrange the equation by multiplying each side by v. My v canceled. I end up with mass by itself, which is here, and then I got v times d, which is this part of the equation. Here's my equation. Okay? Now I just need to plug in the numbers. Mass equals, in this case, density is 19.3 grams per mil. And I multiply that by volume, which was, I converted to milliliters, which was 125 milliliters. Right? All right. Now what happens to my mils? They'll cancel. I end up with grams. Is grams a measurement of mass? Yes, it is. So that makes sense. What's 19.3 times 125? My mass is going to be, let me look. I don't have my calculator. I'll just cheat and look at the answer. It is, there it is, 2,412.5. 2,412.5. That is the answer. Now, what if I said to you, I want it reported, the 2,412.5, I want you to use significant figures to report that correctly. Well, in that case, you got to apply some rules. What are the rules? I'm doing multiplication here, right? So I got to apply rule number 2. Rule number 2 says I'll use the one of the measurements that has the least number of significant figures. So this one has 19.3. That's 3 significant figures. This has 125. That's 3 significant figures. So the least is 3. Because both of them are 3. I got to report this number with 3 significant figures. Okay? How do I do that? I have 2,412.5. That's 5 significant figures there. That would be wrong. I got to report this answer. Instead of 2412.5 grams, I got to report it as 24, and I'm going to round it down to 10 grams. That's not right. Yes, that's right. That would be right. Because the reason I rounded it to 10 instead of from 12 is because this is a significant figure. So non-zero, this is a significant figure, non-zero, this is a significant figure, non-zero, I have 3. That's where I want to be. This 0 is at the end, but it's to the left of the decimal, which means it's not significant. So this one doesn't count. I have 3 significant figures. The answer is 2410 grams, and there's 3 significant figures there, which is the same as the least amount in the equation. Rule number 2. Is that the answer the book gave us? The book says 2410. You could also use scientific notation. They say the other way to say it would be 2.41 times 10 to the third power grams. That's the same number. How many significant figures are there? 3. Scientific notation gives you the same answer. I went with the regular number, 2410. So you can kind of get a taste of how significant figures can really cause you quite a bit of pain. Okay? Because the answer is a little different. Can be a little different to account for them. So anyhow, we're done. I'm going to go over this stuff, this scientific notation stuff on Friday over Zoom to make sure you get it. But in the meantime, I want you to do the on your own problems in the chapter, in the module. Work on them. Practice them. That's your written homework. Practice them. Do them once. Do them twice. Do them 3 times until you're very confident that you know what you're doing. And that will, that's how in chemistry, the secret to chemistry is repetition. Do the problems once, not twice, not 3 times. If it takes 10 times, so be it. That's how many times you do it, and then until it clicks. And when it clicks, it's there forever, and you will do well. It takes reps. That's what you do. Do it on your own. Do them as many times as you need to before it clicks in your head, and you truly understand what you're doing. The answers are right there. You can cheat and just write the answer down, but that's not going to serve your purpose. You need to practice it on your own. Then you look at the answer to see if you got it right. And if you don't, then you look to see where you went wrong and you make the correction, and then you do it again on your own until you get it right on your own. Okay? That's what you do. I will see you on Friday. We'll go over the significant figures part again. Talk to you later. Bye-bye.